In the first video, you have learned a short introduction about the degenerate conics. You have also learned the degenerate conic of type ellipse. These are points and an empty set. For this video, we will be learning about the degenerate conics that are related to hyperbola and parabola. First, let us recall the general equation of a conic. For a conic to be a hyperbola, the product of AC must be negative. In other words, A and C must have opposite signs. We can also transform this general equation into its standard form, and as we have observed previously, the standard form, either of these two equations, must be equal to 1. If the number on the right-hand side is not equal to 1, and at the same time not equal to 0, then we must do something about it using some algebraic manipulations. For example, if this is equal to negative 7, we can divide everything by negative 7 so that we come up with this final form, with this y minus 4 quantity squared all over 7 over 2 minus x plus 2 quantity squared all over 7 over 3 equals 1. And this now becomes the standard equation of the hyperbola. So as you can see, unlike in the ellipse, whenever it is equal to the negative number, it would not necessarily mean that it is an empty set. Rather, we could just easily manipulate it to make it equal to 1. However, if the given equation turned out to be 0 after some algebraic manipulation, then what can you say about this? We know that if the difference of two numbers turned out to be 0, then those two numbers must be equal. So if we choose this first standard equation right here and manipulate it such that we transpose it to the other side, okay? Remember that when m squared is equal to 1, m will have two solutions, namely 1 and negative 1. And that must also be the same process that should be applied in this case. Hence, if we take m to be your y minus k and your 1 to be this whole other right side of the equation, then your left-hand side must be equal to the positive and negative. Okay, so we must have two solutions. Don't forget that. And that would, again, by some algebraic manipulation, would then result to this one. So can we interpret what this is? We actually get to have two different lines given by two different slopes. In this case, they have of different slope. One is positive or going upwards and the other is negative. This makes the two lines not parallel. Furthermore, since they are not parallel but are on the same plane, it must be the case that these lines are intersecting. Now if we consider the second standard equation, again, it must be true that they are equal. So we can transpose it, manipulate the denominator a squared, and then again, this only means that we should have two answers, the positive and the negative. And by transposition, we get this. And the result is the same. That what we actually have is not a hyperbola, but two lines. Now, these two lines are of opposite slopes again. One going up and one going down. Thus, these two lines must intersect. And that is the result of a degenerate conic that is of a form of a hyperbola. We will have two intersecting lines. To wrap it up simply, if the equation turned out to be similar to a hyperbola but is equal to 0 and not equal to 1, then it must be the case that you do not have a hyperbola, but rather you obtain the equation for the asymptotes, which we can also call as the degenerate form of the hyperbola. Let us now proceed to the last part. Let us talk about the degenerate forms of a parabola. Again, this is the general equation for a conic. Now, for it to be a parabola, the product AC must be equal to 0. That means either A or C is equal to 0, or simply as follows. Now let's consider this. If E actually turns out to be 0, what we're left with is a quadratic equation of variable x. If we consider this on the other hand, and let D to be 0, well, we also have a quadratic equation, but this time it is of the variable y. Now, the solutions or solution for these equations actually depend on their discriminant, as you have learned on your grade 8 mathematics. Now suppose t is the discriminant of this equation. We will be dealing with the quadratic equation that is of variable x, but know that all of these arguments would be similar for the part where the variable is y. Because it's just a variable, you can just easily change it. Now, if t is less than 0, again, if the discriminant is less than 0, recall that the equation must have no real solutions. Then it must be the case that there will be no points or coordinates that would satisfy your conic section. If t is equal to 0, then the equation has one solution, and it must be a line. The solution will be of form x equals something, for whatever something that would satisfy the equation. And if t is greater than 0, then the equation has two real solutions. Therefore, we have two parallel lines. Let us illustrate. Supposedly, this is the equation of the conic that you are given. Obviously, this is a degenerate form. Why? Because only one variable exists, and that variable is x. So, using our skills in mathematics that you have already learned, we can do factoring. It turns out that x can be 3 or negative 2. Thus, what we have are parallel lines. We do not have a parabola, but instead we got parallel lines. For this case, if we use our factoring again, which you have already learned, you will see that only one solution exists, x equal to negative 1. And there you have it. You have one line, not a parabola. Now, if we have this equation instead, using the quadratic formula, we get this to be an imaginary number. Thus, the degenerate conic is actually an empty set. So now to sum it up, the degenerate conics are as follows. It could be an empty set, a point, a line, two parallel lines, or two intersecting lines. It is now your task to determine which kind of degenerate conic is being represented on the exercises that are found on your module. If you still have questions, please do not hesitate to contact us, your subject teachers. Thank you and have a great day.